Okay, good morning to one and all. So let me discuss today about this optimum receivers using coherent detection. Okay, so far we have discussed how do we characterize the uh, statistical additive weight Gaussian noise channel, right? We find mean and as well as variance. And yesterday I discussed about what is likelihood function and maximum likelihood function and as well as the probability density function, right? Hope is it possible to say what I discussed? I think I said from my side only. Yes, I would like to hear from your end also. I defined what is the probability density function. Okay, when the symbol mi is sent and xj is received. Yes. And what is that likelihood function? Then log likelihood function. Maybe it is difficult to say with the equations. At least what is what? Is it possible to say? Yes, are you aware what is that? What I discussed yesterday? Yes, say yes or no, so that I can proceed further. Able to grasp the concept what I said yesterday? Hello.
Yes, sir.
What about others? Skanda says yes. What about others? I'm asking.
Yes, sir.
Okay. Okay. Then let me continue. I think it will give you overall idea what I discussed yesterday also, and today what I'm going to discuss. Hope the slide is there. No? So today we are going to discuss about the maximum likelihood decision rule. What is that? What is the maximum likelihood decision rule? And then we are going to discuss about two receivers. Okay. One is correlation receiver. This correlation receiver has two subunits. One is known as detector or demodulator, and second subsystem is the maximum likelihood decoder. Okay, so together these two blocks are known as the correlation receiver, and the next one is matched filter receiver. So these two topics are very important. I can assure you that definitely there will be one question on this topic for 8 to 10 marks. Okay, out of these two receivers, either correlation receiver or the matched field receiver, any one question will be there. And these are the most frequently and more popular type of receivers which are used in the communication system, especially digital communication system. So that is why so try to give attention, concentrate also, and try to ask questions if you have any difficulty at any point of time understanding. Okay, so examination point of view also I'm saying it is important. You just go back and see the question papers, you will understand how frequently they ask. Every year there will be question on this topic. Okay, fine. So to begin with that, so just I take I think looking at this, hope we are able to understand all these things which are already known. So I made now slideshow. Is it visible?
Yes,
Yes.
sir.
Yeah. So just it is a recap. What I can say is just it is a recap of what I discussed so far. Right. Hope we are able to see the first is what this is the additive white Gaussian noise model of the channel. Right. So I started with this. So x I of t is the transmitted signal. I said si of t is the transmitted signal, and I denote the white Gaussian noise with w of t. So x of t is the received signal. How they are related, right? How the received signal is related with the transmitted signal. So which we have written, right? Which we have already discussed. So x of t will be equal to si of t plus w of t. I said, what is that si of t? It is a transmitted signal for symbol mi, and w of t is the additive white Gaussian noise. and this additive white Gaussian eyes have zero mean and a power spectral density of n naught by 2, right? So how do I represent this in the form of vector? That is the received signal x of t. I represent that as a vector x, right? So yesterday I discussed that x is equal to x1, x2 and so on up to xn. And similarly, the signal vector si can also be represented as a vector, right? So that is from si1, si2 and so on up to sin. We know this, right? How do we represent the signal, uh, transmitted signal as a vector? Then this is the noise. So that is also is expressed in terms of vector. So this we call as a observation vector or vector model of the channel. Okay. So if I say vector model of the channel, we are going to express output of the channel, input of the input to the channel, and as well as the additive white Gaussian noise in the form of vector. Fine. And even this diagram also you are aware, right? Maybe I told with a different name. I called, I think, as analyzer. Hope you are remembering this diagram. Instead, yes. So what is there here? So x of t is a received signal, right? So which will be passed through multiplier followed by an integrator. I call this multiplier followed by an integrator is known as the correlator, right? So here I have n number of correlators. Output of each correlator is what I write x1, x2 and so on up to xn. So this is the received signal vector, right? Received, that is x, capital X, what I used to say. So which is equal to what I is right, s I1 plus W1 is x1 and x2 is equal to si2 plus w2 and so on up to sin plus w1. So this is the what output of correlator output, right, in the additive white Gaussian channel. So and already I said we found that what is the mean of this output vector x, right, which is equal to sij. And what is the variance? I said it is n naught by 2. Okay, so this is the fact what I discussed in the previous two classes, right? Fine. Yeah. So this is what I discussed yesterday. Okay. So that is what signal detection in the additive white Gaussian noise channel. What I said, and we already know that the output of the correlator, that is the vector x, are statistically independent, right? So we can express the conditional probability density function of the vector x, right, if the uh, transmitted signal si of t or with the corresponding symbol mi, where the value of I can vary from 1 to m, was sent, right? So that is what I said, it is the product of the conditional probability density functions of its individual elements. Okay, so this is what the conditional probability density function when the symbol mi is sent and x is received, right, which is equal to what, the product of the conditional probability density functions of its individual elements. So that is why first one fx I write, so x1 slash, that is a mi is transmitted, x1 is received, right? Similarly x2, x and so on up to xn, right? So this I said, this product of individual uh, that is the product of the conditional probability density function of its individual elements can be rewritten like this. That is the product, no? So pi j is equal to 1 to n fx j of xj slash m, right? So this is what the conditional probability density function of the random variable xj. And yeah, with respect to I said Gaussian probability density function, right? We found fxj of xj slash mi is equal to this, right? 1 by root of pi n naught e power of minus 1 by n naught uh, xj minus sij whole square, right? Where j value can vary from 1 to n and I value can vary from 1 to m, right? So, and after simplification, means after substituting this value in the above expression, means in this equation, I got this one, right? So I express it as what, pi n naught to the power of n by 2 e power this function. And after this, right, after this, what I said, I defined some of the terms, and before going to that term, what I said is we will be able to uh, So of course, I might not have used the word as a theorem of irrelevance, but I told this is the equation 7. What I said, right? X of t is equal to summation j is 1 to n xj pi j of t plus x of t. So it is possible to means to say what is that statistical uh, satisfaction, right? So with respect to only this one, first term, right? So that is what the meaning of the previous equation, what I said. So the signal detection in additive white Gaussian noise is concerned only the what projection of the noise onto the basis function of the signal set, that is Si of t, right? So that will affect the sufficient statistics of the detection problem. Okay, and the remainder term means this one w dash of t is irrelevant, what I wanted to say. Okay, so the correlator output will be determined by the received signal x of t are the only data that are useful for the decision making process, not with the noise, right? The correlator outputs which are determined by the received signal x of t are the only data that are useful for the decision making process, I said. So I think this also I told about this. What is this one, right? So it is what any random variable, right? Say w of tk. So derived from the noise process w of t by the sampling at time tk is statistically independent of the random variable xj, right? That is what we found, how they are statistically independent. Uh, yeah. So I think, yeah, yesterday I discussed about this likelihood function and as well as log likelihood function. I am just going once again about that what I said yesterday. So what I said, what is the signal detection problem? What I wanted to say is, if the observation vector x is given, right? How do I estimate the message symbol mi? Okay, that is responsible for generating the vector x, right? So to understand that, what I said, we are going through this likelihood function and log likelihood function, right? So how do I find or define the likelihood function? So the likelihood function is denoted by small l of m suffix I. Okay, so I represent the likelihood function by what? The variable l of m suffix I, right? How do I define that? So l of m suffix I, which is equal to this one, f x of x is sent, x is received when mi is transmitted, right? So this is what the conditional probability density function, right, of the vector x. So the conditional probability that the signal vector x is obtained when the symbol mi was given or transmitted, I think I substituted the value of this one, right? Means I defined the previous equation, right? That is what the likelihood function I say. So this is how defined fx of x slash mi is equal to pi n naught to the power of minus n by 2 e power this. So here, since it is it is having an exponential function, and this equation seems to be complicated. Okay, to simplify this understanding and as well as the computation of this, what we do, we go for the log likelihood function. So the log likelihood function, which is defined as, and it will be denoted as capital L of m suffix I. Okay, capital L of m suffix I. So which is equal to what? Natural logarithm, right? Natural logarithm of the likelihood function. So that is why I written ln of L of m suffix I, right? So this also I discussed yesterday. And when I take the natural logarithm to this equation, right, what I get, uh, that will be my log likelihood function, right? So L of m suffix I, capital L of m suffix I is equal to minus 1 by n naught into summation j is 1 to n xj minus sij whole square. So here I said the first term also there, which is constant. What is that first term? That is minus n by n naught by n by 2. It is minus n by 2 into ln of pi n naught, right? So and that is neglected because it is independent of the transmitted symbol. Okay, and as I said yesterday, it is not having any relationship with the transmitted symbol. That is why we uh, don't consider the first term, which is constant. Only we say what is the likelihood function is this minus 1 by n naught summation j is 1 to n xj minus sij whole square. Fine. So I think we have discussed it till this yesterday. Hope is this clear what I said again? Hope people are there with me.
Yes, sir.
Okay. So the log likelihood function, okay, I said, yeah, the log likelihood function bears a one-to-one relationship to the likelihood function. So this is the log likelihood function, no? And this log likelihood function, I'm saying, bears a one-to-one relationship to the likelihood function. Okay, these are the two reasons. First one is, by definition, what I can say is a probability density function is always non-negative, right? And it follows that the likelihood function is likewise a non-negative quantity. Then the logarithmic function is a monotonically increasing function of its argument. Okay, so monotonically increasing function of its argument. That is what the logarithmic function is. I hope you are able to visualize that. Monotonically increasing means, any one of you can say how the graph will be. Yes, quick response I need. So far I discussed the yesterday till this. I defined what is likelihood function and what is log likelihood function. Okay. So now let me take about the optimum receiver, right? Using coherent detection. I said no, it has two things. One is maximum likelihood decoding. So first let me discuss about that. What is that maximum likelihood decoding? Okay. So just have a look here. What is there? So I am considering a time slot, that is the symbol duration, okay, which is equal to t seconds, right? So I will be transmitting one of the m possible signals in that duration. Okay, if I consider a time slot having a duration of what, t seconds, in that t seconds I'm going to uh, transmit m possible signals. So what are those m possible signals? It is s1 of t, s2 of t, and so on, sm of t, with equal probability. So with, if I say with equal probability, its value will become 1 by m. Okay. So here m possible signals means I think we will be able to understand in the coming lectures. If I say BPSK, I can transmit 0 with one phase and 1 with another phase. That is 0 degree with phase shift. Okay. So I can transmit if I have a sine signal for representing symbol 0, and symbol 1 will be represented with 180-degree phase shift. Okay. So like that, if it is for FSK, I can transmit symbol 0 with one frequency and symbol 1 with another frequency. So symbol 0 transmit with frequency f1 and symbol 1 I transmit with frequency f2. Like that, in case of QPSK, since it is a quadrature phase shift key, I will be able to transmit 4 symbols of information with 4 phase shifts. That is why it is called quadrature. Okay, it means I can transmit 2 symbols, that is 2 digit as one symbol with 4 possible phase shifts. In that sense, here I am generalizing it to m possible signals, right, with equal probability of what, it will be 1 by m, right? So just have a look about this diagram. So this is the signal constellation diagram what I have written here. So pi 1, pi 2, and pi 3. In this, what I have represented is two things. One is the signal vector. Okay, so this point is a message point. So I say that is a signal vector, right? So I represent the signal vector by s suffix I. So si is the signal vector, or I can say is the transmitted signal point, right? So that is what the message point. This is without noise. Okay, this is the message point without noise. Fine. So the correlator output when Si of t alone is provided as input, what I can say. Hope you're able to see this message point. I took pi 1, pi 2, pi 3. In this space, I'm representing the message point. So I call that a signal vector. It is what? This is the transmitted signal point with no noise, right? What I wanted to say is this is the output of the correlator only when signal input is there without noise. And one more I have written here, the received signal point. This point is the received signal point. I write that with the observation vector x. Okay, so observation vector x is the what received signal point. This will be having signal plus noise, right? Si plus w, and this is what I shown arrow is the noise vector, that is w. Yes, able to visualize this diagram, understood this diagram? I represented the message point, right? So without noise, and then the received signal point. So the received signal point, that x will be what, which is equal to Si plus w. So that is why signal point plus noise will be there. So this much is the noise vector, what I can say. So this is a noise vector, and this one is a signal vector, and this one is the observation vector, right? So that is due to the received signal point. Fine. So here the observation vector x, right? So this will differ from the signal vector. So because of what? Because the noise will be added in the channel, right? So because of that, the received signal point will be slightly away from the original message point. Hope you are able to understand what I am saying. Hello?
Yes,
Yes,
sir.
sir.
Yeah, I said the received signal point will be slightly different from the original message signal point. Because of what? Because of the noise which is added at the channel, right? So that is why this diagram is shown here. So this is the message point, and I say is the signal vector, and this is the noise vector, which is denoted by w, and this one is the received signal point, so which is denoted by the observation vector. And I said the received signal point is slightly different from the message point because of the noise. Okay, so the observation vector x differs from the signal vector by the noise vector, right? And even the orientation of this noise will be random, right? So it may lie anywhere inside this Gaussian distributed cloud. What we say is, so around this, I will show that cloud. What is that noise cloud? I think which is surrounded at the center of the message point. I think no, there. Okay, oh, noise cloud is not there. Mm, okay, so actually I removed one diagram. Uh, yeah, okay, I will, I think, take up that. Fine. So this is what the noise cloud. In that there will be a message point. So surrounding that, there will be a received signal point. It is fine. So now let us try to understand what is that maximum map rule. Okay. Yeah. So I was telling maximum a posteriori rule, right? Maximum a posteriori probability rule is known as the map rule. Okay, let us try to understand what is this maximum a posteriori probability. So map means that maximum a posteriori probability rule, and another one is what? Maximum likelihood rule. So let us try to understand what is this. Okay, so if the observation vector x is given, okay, if the observation vector x is given, then what we need to do? We need to perform a mapping from that x, okay, to an estimate m cap. Okay, m cap is the what? Estimation of the transmitted symbol. What is the transmitted symbol? That is m suffix I. Okay, m suffix I is the transmitted symbol. I need to estimate that. That estimation is known as m cap. Okay, how do I estimate this? I estimate that from the received signal vector x. Okay, so how do I do that, and in what way I should do? I need to do that by minimizing the probability of error in the decision making process. Okay, I repeat once again. If the observation vector x is given, I need to do what? I need to perform the mapping from that observation vector to estimate m cap of the transmitted symbol mi in such a way that there should be what? It should minimize the probability of error in the decision making process. So probability of error should be minimum. Okay. Then I say it is fine. Okay. How do I define that? How do I define the probability of error? So this is how I define. This is the definition of the probability of error. So I denote that as what? Probability of error, that is p suffix e of this mi is the what? Is the symbol transmitted. Okay, mi is sent and x is received. I read like this. Okay, this is a conditional, right? So p suffix e is the what? Is the average probability of error, right? So which is equal to what? When symbol mi was sent and x is received. So which is equal to what I can write? 1 minus p of mi is sent and x is received. So what is this p of mi is sent and x is received? This is the, any one of you can say what is this one? P of mi sent and x is received. This is the average probability of correct decision. Okay. Yes, hope are you able to understand what I'm saying? P of mi is sent and x is received is the what? I said it is the average probability of correct decision. I can denote this by this entire term by p suffix c. That p suffix c indicates is the average probability of correct decision. Then how do I define the average probability of error? That PE is equal to 1 minus PC I can write. So 1 minus PC. PC is nothing but this one. Okay. Average probability of correct decision. So what is the statement here? I need to minimize this, right? So this is LHS and this one is the RHS, right? How do I minimize this? That is what, no, here minimize the probability of error in the decision making process, right? So when can I say this is minimum? Yes, quickly I need response. I think this is what I need your involvement here. So this is what? This is the probability of error, right? How do I minimize this? Yes, any one of you can say by doing what? By I will be able to say this is at minimum level. Yes, what is there? What is LHS and what is RHS? See, LHS is equal to 1 minus this is average probability of error, no? So which is equal to 1 minus the average probability of correct decision, right? If I maximize this correct decision, if I maximize the average probability of correct decision, that is, if I maximize the second term of the RHS, then I can say this will be at minimum, no? Yes or no? Hello? No response only. Yes, my dear students, are you there? My network is there, I don't know.
Sir, yes, sir.
Yeah, what I wanted to say here is, if the observation vector x is given, I need to map that to, I need to estimate m cap, right, of the transmitted symbol mi in such a way that there will be minimum probability of error in the decision making process. So I said this is the average probability of error. Okay, average probability of error. So which is equal to, I said, 1 minus the average probability of correct decision. Okay, this is the average probability of correct decision. I said this has to be minimized. The LHS term has to be minimized. Then only I can say the receiver is good. Okay, if the probability of error is less, right, then I will be able to say I will be receiving 100% information correctly. Okay, if I am transmitting 1000 bits, if I am able to receive all the 1000 bits exactly, then it is an ultimate ideal receiver. Okay, if I receive out of 1000 bits 990, then there is some amount of error, right? Okay, so what I said, this has to be minimized now. To minimize this, I need to maximize this one. Okay, what this maximum a posteriori rule says is, what is that rule is? To do that, first we need to set, I think it is m cap is not visible, please have a note of this. So we need to set m cap is equal to mi. Okay, we need to set m cap is equal to mi if the probability of what is this mi is sent and x is received is greater than or equal to probability of the message mk is sent and x is received. Okay, for all the values of k equal to I. Okay, where the value of k can vary from 1 to m. So this rule is known as the, I said what, maximum a posteriori decoder rule. Okay, if I implement this rule, okay, if I use a system to implement this rule, is known as the maximum a posteriori decoder, I say. Okay, so what is that map rule is? Maximum a posteriori probability rule is what? I need to set m cap is equal to mi if p of mi is sent and x received is greater than or equal to p of mk is sent and x is received. That is what the for all the values of k equal to I. Okay, that is what the maximum a posteriori probability rule. Okay, and we can restate this maximum a posteriori rule in other way also. So there are other possible ways to say this decision rule. So this is what we say the optimum decision rule is. What is that optimum decision rule? Set m cap is equal to mi if the probability of message symbol I is sent, x is received should be greater than or equal to probability of, okay, message mk is sent, x is received. Okay, our goal is what? We need to maximize the average probability of correct decision so that the average probability of error will be minimum. Okay, so as I said, this map rule, that is maximum a posteriori probability rule, can be restated in terms of prior probabilities of the transmitted signals and the likelihood functions. So in what way I can say, I will just tell, I will skip some of the part which I feel you may not be required to understand this point. So what I wanted to say, this is this clear, this rule, what I said, what is the optimum decision rule? So the goal is this, we need to minimize the probability of error. How do I minimize that probability of error? By maximizing the average correct, uh, by maximizing the average probability of correct decision, right? So for that, what is the optimum decision rule? We have to set m cap is equal to mi if the probability of this mi is sent, x is received should be greater than or equal to probability of mk is sent, x is received for all the values of k equal to I, right? So this is what the map rule, what we say. And fine. So I already defined what is log likelihood function and other things, right? So what I wanted to say with respect to this is, I said no, it can be restated as in terms of the prior probabilities of the transmitted signal and the likelihood functions. What is that? So let us set m cap is equal to mi if this is what is the product, right? Product of the uh, pi k is the what is the prior probability of the transmitting symbol, right? And f x of x is sent, x is received and mi is sent, right? Is the conditional probability density function of the random observation vector x, right? Given the transmission of the symbol mi, or I can say mk, right? And the denominator here, fx of x, is the unconditional probability density function of x. So this can be restated in terms of the log likelihood function L of mk as what? Because the denominator function is what, independent of the transmitted symbol, and what I can say, the prior probability pi k can be made equal to pi I when all the source symbols are transmitted with equal probability, and the conditional probability density function, this one fx of x plus mk, bears one-to-one relationship with the log likelihood function, as I said, right? So with that, what I can say, set m cap is equal to mi if L of mi is maximum for k equal to I. Okay, set m cap is equal to mi if L of mi, okay, is maximum for k is equal to I. Is this fine? So here I have written L of mk, right? Because with respect to this one, right? So set m cap is equal to mi if L of mk is maximum for all values of k equal to I. So the same thing, whatever the map rule I said, na, that can be restated in terms of the log likelihood function in this way. Okay, I don't know how many of you are able to get this point. Is that clear? So the map rule is expressed in terms of likelihood function. Okay, to maximize the likelihood receiver. So what I said, set m cap is equal to mi, right? Set m cap is equal to mi if L of mk is maximum for k equal to I. Okay, so this is what the maximum likelihood rule, what to say in terms of words. What is that? So according to the decision rule, whatever I said, set m cap is equal to mi, right? If L of mk is maximum, right, for all values of k equal to I. So according to the decision rule, what I can say, the maximum likelihood decoder will be computing the log likelihood functions as metrics for all the m possible message symbols. Okay. So according to that rule, what I said, the maximum likelihood decoder computes the log likelihood functions as metrics for all the m possible message symbols and compares them and then decides in favor of the maximum. That is what the maximum likelihood decision rule is. So the maximum likelihood decoder is a simplified version of the maximum a posteriori decoder. Okay, in that the m message symbols are assumed to be equally likely. So this is what we say as the maximum likelihood decision rule. Okay, you will be able to get a clear picture what I told in terms of sentence or words here with respect to diagram. If I show that, then you will be able to visualize this statement. So let me take up that. Okay, so then the same thing, no? So here I think how I say the map rule, how that can be restated in terms of log likelihood function. The same thing can be interpreted in a graphical manner. So how do I interpret that maximum likelihood rule in terms of graphical interpretations? Let me just say that also. So what I do here is, uh, so hope able to see this diagram, signal cancellation diagram. So this is pi 1 axis and this is pi 2 axis. Here I have divided this into different regions, okay, with the decision boundaries. I took two decision boundaries. This is one decision boundary and this is another decision boundary. So I made this is one region. So I represented that as region Z1, and this has region Z2, and this is region Z3, and this one is region Z4. I have four message points. Means I'm considering four message symbols. So one on pi1 axis, that is message point 1 with value root of e, and another one is the message point 2, that is on the pi2 axis, that is root e, and third one is the message point 3 on the negative of the pi1 axis, which is minus root e, and message point 4 lies on the negative of the pi2 axis, which is minus root e. Okay, so means I am considering here I have four message symbols. I divided this entire space into different regions. Okay, then how do I map that, and how do I estimate that? Okay, this is what the received symbol is. Okay, okay. So what if the observation vector lies on the decision boundary? So that is the question, right? So hope we are able to correlate the previous diagram what I have shown there, message point, then received a signal point with noise, how the received signal point is different from the original message point, right? So here I'm divided this into different regions. Okay, so four regions. So there is a question, right? If the observation vector lies on this decision boundary, how do you take a decision? So it is nothing but flip a coin and decide. Okay, so that could be the solution if the message point lies on this decision boundary. Fine. So here what I wanted to say is, how do I interpret that maximum likelihood rule with this with respect to this graphical interpretation? So this is what my log likelihood function, right? So the observation vector x lies in the region zi. I generalized here, the value of I can vary from 1 to m. So here I have taken the value of I is 4. That is why I written 4 regions, z1, z2, z3, z4, right? So observation vector x lies in region zi if L of mk, that is log likelihood function of the symbol mk, is maximum for k equal to I, right? For k equal to I. So what is that maximum likelihood function? Log likelihood function. This is how I define log likelihood function, right? So L of mk is equal to this minus 1 by n naught into summation of j is 1 to n xj minus skj whole square. So when this log likelihood function attains the maximum value, when it attains the maximum value, right? So when it can attain the maximum value, when this log likelihood function can attain the maximum value, any one of you can say when it can attain the maximum value? Yes, any one of you can say when this log likelihood function can attain the maximum value. So it can attain the maximum value when this summation term is minimized, okay, by the choice of k is equal to I. So when k equal to I, so the value of this will be minimum. That is when xj is equal to skj, right? When xj is equal to this, the summation term becomes 0, right? Then it will be maximized, right? Yes or no? Because it is a log likelihood function. Yes. So log of 0 will be 1 maximum. Hope you are able to understand what I am saying. The observation vector x lies in the region zi if the log likelihood function is maximum for k equal to I. So I said when this log likelihood function can be maximum when this summation term is minimized, okay, for the value of k is equal to I. Fine. So the observation vector x lies in the region zi if this summation term is minimum, right? If the summation term is minimum for k. So I can express this summation term, summation j is 1 to n of xj minus skj whole square as square of the norm of the distance between the received signal vector and the signal vector. So I think this I discussed when I was discussing about how the signal vector and its length is computed, right? So I can say the summation j is 1 to n of xj minus skj whole square is equal to what? Square of the norm of the what? Difference between the received signal vector and the transmitted signal, that is sk. Okay. So this is what the Euclidean distance between the observation vector x at the receiver input and the transmitted signal vector sk, right? So this we know. So this has to be minimum. This has to be minimum means what? So observation vector x lies in the region zi if the Euclidean distance is minimum, right? If the Euclidean distance is minimum for k equal to I. So what this maximum likelihood rule says is choose the message point closest to the received signal point. Then I will be able to estimate the received, I will be able to estimate properly the transmitted symbol which is equal to the received one. I don't know to what extent people are able to get this point. This is what how we say the graphical interpretation of this maximum likelihood rule. I think with respect to this diagram, I think again we have to come back to this, right? So here now, I said this is the message point, right? And this is the received signal point. So this is the message point and this is the received signal point. So this received signal point should be as close to this message point. Then I can say I am able to estimate this is what the transmitted symbol is correctly, right? If the distance between these two is large, then there will be a choice of taking a wrong decision about the received symbol. Okay, about the what is transmitted symbol. Fine. Yes, I don't know. People are not responding whether they are able to grasp this idea or not, because it is a very, very important concept. What I wanted to say, but it is slightly tricky. But I think with respect to this much of content and explanation, I hope we will be able to grasp. So I need response from you people. Is it okay, or you want me to say in a different way? Yes. Do you have any questions? Hello. Yes, nobody is responding. I don't know whether people are there with me or I am there with you people or not. I don't know. Hello.
No doubt, sir.
No doubt. Thank you. Able to understand Karunya.
Yes, sir.
Okay, thank you. Then, so with that, let me go ahead. Okay, so I told how do we interpret graphically this maximum likelihood rule. Then I think so that is what is done. Okay, of course, I have not finally concluded. One more equation is there. I will come to that. I think I will. Yeah. Uh, Fine. Okay. So what I said, that summation part, no summation part, that is j is 1 to n of xj minus skj whole square. Right. This can be expanded by using a minus b whole square formula. Okay. So it is that. It is the expansion of a minus b whole square, that is a square plus b square minus 2ab. So what is the first term? So this is the energy of the uh, signal vector, what I can say, that is the energy of the first term is the energy of the received signal, and which is independent of the index k. Okay, the first term is the energy of the received signal and which is independent of the index k. So I can ignore this. I can ignore this term because k is not present here, right? And the third term, no? So this is the energy of the transmitted signal, energy of the transmitted signal, that is Sk of t. So this is how we define energy of the signal. Ek is equal to summation j is 1 to n s square kj is the definition of the energy of the signal. So I can say this is the energy of the signal. And what is the middle term? Any one of you can say what is middle term is known as? That is minus 2 into summation j is 1 to n xj s suffix kj. What we call this middle term is, I think you have studied about inner product, right? Are you aware of inner product? Hello, no response. Yes, my dear students, please respond. Have you studied inner product? I think it is, you might have studied in a linear algebra about the inner product. So this is, I can write x transpose sk of t, right? So this is the inner product. So I, by neglecting this term, no, I can rewrite, means I said I need to minimize this term, right? To say that I am maximizing the log likelihood function. So I can restate this statement. The observation vector x lies in the region zi if this summation, okay, this term minus 1 by 2 ek. What I said, ek is the energy of the signal sk of t. Okay, this term is maximum for k equal to I. Okay, I can say the observation vector x lies in the region zi. That I value can be 1 to m. Okay, I can find that the observation vector lies in the region zi if this one is maximum complete thing. That is, I rearranged this and I got this one. Okay, minus 1 by 2 ek summation j is 1 to n xj skj. So this is the inner product. What I said, this has to be maximum for k equal to I. So this is what the other way of saying the decision rule. Okay. Okay. So with respect to that, hope let us, because this is what the concept what we use in receivers. Okay, for estimating the transmitted symbol. So based on that, I said there are two types of receivers. Based on the map rule, there are two types of receivers. One I said correlation receiver, and another one I said it is a matched field receiver. So here what I have shown is the correlation receiver. In the two parts I said, no, one is the detector part, another one is the maximum likelihood decoder. Okay, so what the detector is, here x of t is the received signal, right? You are aware of this diagram already. That is why I don't have to say again much about that. So what is this? X of t is the received signal that will be passing through the correlators, that is multiplier followed by an integrator to get the observation vector x. Right, so I am using n correlators here. So output of each correlator I will be denoted as what, x1, x2 and so on up to xn. So this is the received vector x. So that is the first part, detector or decoder I said, right? Detector or demodulator. And I am feeding this vector x to the next subsystem. What is the next subsystem? So I am passing that vector, received vector x, through what, inner product calculator. What is that inner product calculator? So again, means I am getting this term. No? I need to get this first term, that is inner product. So I do that by doing this one. That is, received vector is multiplied by the signal vector, that is x1, s2 and so on up to sm. Then do that accumulator. So together output of that will be this one, x transpose s1 I can write, that is x transpose sk. So where the value of k can vary from 1 to m. So like that I have m number of these things. Then the next is what, this minus 1 by 2 ek is there, right? I need to balance this. So that is why I'm doing this. This inner product minus that energy 1 by 2 E1. Output of that, of each of these things will be what, given to the block, which will be taking the maximum of these. Okay, I have m of this type of things. Out of that, it will take the maximum. That will be going to say that is what my transmitted symbol. That is estimate m cap is equal to, means m cap is equal to mi among what? It will select the largest of these things. Okay. So here I expressed this in terms of vector, that is x1 right, column vector, and this also as a si1, si2 so on up to sin, then minus 1 by 2 ek. So this is what the correlation receiver is all about. I think with this I will stop. Okay, so let me so just 1 minute I will take the attendance.